Okay, welcome everyone to the EOL seminar. Today our speaker is Robert Menke, and he's from the Technical University of Denmark. Robert did his master's in engineering physics at the University of Oldenburg in Germany. And after that, he moved on to Technical University of Denmark, where he's currently working on his PhD thesis, which he will hopefully finish at the end of this year. He has spent the last half year here in Boulder with the Advanced Study Program here at EOL. And before that, he also spent a semester at CU Boulder, where he got the Otto Monstedt Scholarship. And the topic of his PhD thesis is on lidar scanning over complex terrain. And we are excited to hear his results today.
Yeah, thanks for the introduction. So, hi everyone. I'm going to talk. I hope you didn't read the abstract too closely, because I just realized an hour ago that I slightly moved some topics more to recent work that I did. But it's still, the overall topic is still the same. I'm going to talk about Doppler scanning of flow over complex terrain, mainly focusing on the Perdigão measurement campaign in Portugal. And this work was carried out in the scope of the New European Wind Atlas. Jakob Mann, my supervisor, gave a detailed talk about this here, I guess 4 or 3 weeks ago. So just give a very quick overview to the project. The aim was to map the wind resources over Europe, mainly with focus on wind energy production. There was a very old wind atlas from the 80s, which is basically just based on 10-meter measurement masts. So this is now, the goal was to increase the accuracy and the resolution significantly. And the project was mainly basically consisting of 3 components: measurement campaigns used as validation for flow models, then the development of a model chain, and then finally basically the production of the wind atlas for Europe and to publish it. In the results of the project, you can see on the right the plot. These are the mean wind speeds calculated by WRF over Europe. And all this data is accessible via the web page that is linked down there. And there's an option to zoom in, get some different data products. So it's nice exploring that. And the project ran over 4 years, so it finished earlier this year, and the results were presented at a conference in Brussels. And partners in this project were industry and university partners from different countries in Europe. But today I will focus on basically only on the measurement campaigns, and actually in specific only on one measurement campaign, the measurement campaign in Portugal, the largest one in the NIVA project, with the goal especially on improving our understanding of flow over complex terrain, and with the aim to generate a data set that can be used for model validation, but also to study flow phenomena in complex terrain. And maybe you noticed I used the plural in the heading. There was a pilot campaign in 2015 at the same site, which was basically only carried out by DTU, the Technical University of Denmark, and the University from Porto in Portugal, which was basically only a multi-lidar measurement campaign focusing on wake measurements and resource assessment in complex terrain. And there's an overview paper describing the results and findings from this campaign, which we also used a lot to design scanning trajectories in our measurements for the campaign 2 years later in 2017. But first I want to focus on the question, why are we so interested in complex terrain? I mean, it's obvious that flat terrain sites, as in northern Denmark and Germany, are optimal for wind energy production, where winds are more steady and turbulence levels are lower. But the reason why we're actually also interested in complex terrain is that, as you can see here from the slope map, terrain slope map from Europe, that many areas in Europe and also on the world are actually complex terrain. There's a study that says that 70% of the land surface is considered as complex. So it's important to know how wind turbines operate in these conditions and how we have to design them. Especially also focusing on the fact that looking here at the installed capacity represented by the circles in Europe, that you can see basically that Denmark and North Germany, you can't see it anymore, which also means there are almost no sites left for wind turbines. And basically we have to move to other terrain that is more difficult and less optimal for turbines to increase the installed capacity, which also became more feasible in the last years as the price of wind turbines dropped significantly. So it's more economically interesting to also have turbines in complex terrain where normally wind speeds are lower and fatigue loads are higher. And then another point that was like key factor in the topic of this talk are lidars. So why do we want to use lidars instead of traditional met masts? The strongest factor is that lidars are much easier to deploy. On this picture you see a measurement mast that was installed in Portugal, a 100-meter mast, and you can see that the terrain had to be evened out around the masts, and it took several weeks basically to erect these masts. And then in comparison, actually on this resolution it's very hard to spot. There's a scanning lidar just in the corner of the picture, so you could just see the dimension. It takes half a day to deploy one scanning lidar and 2 weeks or more to erect a mast of 100 meters. And then another, especially in complex terrain, an important factor is that scanning lidars allow us to measure entire flow fields compared to single profiles. So we can actually capture more complex phenomena and it's easier to understand them. For example, like this atmospheric waves that we saw during many nights of the Perdigão campaign, which would be actually very hard to detect if we just have single profiling instruments, if it's masts or profiling lidars or balloon launches. Especially as these waves were standing, it's very hard to see from a single profile that we actually have these waves that were present over the site. Okay, but what happened exactly 2 years in Portugal? In total, so we had a lot of instruments at the site, a very high density, 50 measurement masts, 26 lidars, of which 19 were scanning lidars, and a very wide spectra of different other instruments, from temperature profilers, radar profilers, balloon launches. We had acoustic measurements that were concentrating on the noise that the turbine at the site was making. And some of the masts operated for a year, early 2017 to early 2018, but most measurements were collected during the intensive operation period from the beginning of May to mid of June. And during this period, also most of the project partners that came from Europe and the US were present at the site. And the reason why we went explicitly to this site in Portugal was this unique terrain feature of these two parallel ridges that you can see here in the picture, which make the terrain very complex but still gave it like an understandable structure so we could expect certain flow phenomena. A bit more in detail about the topography. So these two ridges, we call them the northeast and southwest ridge, were almost perfectly parallel over a distance of about 2 kilometers. And they were 1.5 kilometers apart with a valley bottom to ridge top height of 250 meter. And also perfectly was that the prevailing wind directions were perpendicular to the ridges, so from the northeast and from the southwest. And then I copied this diagram or this picture from a bumps paper, an overview paper for the campaign, where basically different flow phenomena that we expected previously to the campaign are basically sketched. So what we could expect at this double ridge location. So we would see blocking effects, then interaction of the terrain and the wind turbine wake. We had a single wind turbine that was located on the southwest ridge, some waves, katabatic and anabatic flows, recirculation zones, and then gap flows. There was a small gap in the northeast ridge. And we had different groups focusing basically on different phenomena, really concentrating the measurements. There was, for example, DLR concentrated all the measurements on measuring the wind turbine wake. And from the DTU participation, we basically focused on, or mainly focused at how we can characterize or measure wind resources for wind turbine applications, for wind energy applications along the ridges, how recirculation zones that would develop behind the ridges would affect downwind locations, possible downwind location of turbines, and on the formation of atmospheric waves, as you could see earlier. And today I will mainly focus on the first 2 points, starting with the wind resource estimation with scanning lidars. And quickly want to repeat why we think it's a good idea to use scanning lidars. I already mentioned that they're more easy to deploy. And also with, like in 2 scanning lidars, if we combine and if we synchronize them, we actually can cover very large areas, especially in complex terrain, which is important, which is especially more important in complex terrain, as the spatial variability is much higher as in flat terrain. In flat terrain, it will be enough to have one mass and you could interpolate from there over a large area, which is not possible at all in complex terrain. So it's important to have this flexibility of having many measurement points covered, which is easily doable with a dual Doppler lidar system, which makes lidars compared to measurement mass much more cost effective. Obviously there are also disadvantages. We hardly can measure turbulence with scanning lidars or with lidars in general. So this is something we would miss or would need still measurement mass, at least at some locations, to capture turbulence or more high frequency data. But coming to the assessment of wind resources at Perdigão, we especially designed a scanning scenario for this to measure the wind resource along the 2 ridges. It's here, the lidar measurements are represented by these blue lines along the ridges. We had 2 lidars on each ridge following these trajectories that were exactly 80 meters above terrain height. So it was a complex trajectory following exactly the height profile of the ridges. And we were mainly interested in the questions of if there is a change of the wind resource along the ridges. So does it matter if, like, where would we place a turbine on a ridge? And how does the downwind ridge affect the upstream ridge, or the other way around for opposite wind direction? And we can see an effect on the wind resource that the southwest ridge was slightly higher elevated. It was not much difference, but it was slightly higher. So we were interested to see really the effect of these points, of these questions. And the lidars that we used were long-range wind scanners, which are basically modified Leosphere 200S pulse Doppler lidars. We run a special software that was developed DTU, which allows us to do these complex trajectories and also to synchronize them in a better way. And I guess this animation explains best how we measured. So these 2 lidars followed in a synchronized fashion these 2 traverses along the ridges. And the transects were 1.8 kilometer long, had a very low elevation angle, which was optimal. So we actually choose, especially for keeping this elevation angles low, we placed them on the ridges, on the opposite ridges. So our measurements would be less affected by vertical wind components that are pretty high in complex terrain. So we could really measure the horizontal wind, which is basically the wind that is also converted by wind turbines to energy. And we designed acquisition time of the lasers and the scanning speed so that we had a measurement point every 20 meters, but we scan continuously. And the LiDAR, one scan took about 45 seconds, and the LiDARs had an average volume of about 30 meters. And we carried these scans out for 10-minute periods, 2 10-minute periods per hour. During the other time, we ran other scenarios focusing on different tasks. So before I come to the analysis, I want to cover quickly how we process the data. Here on these plots, you see 10-minute average data of a single LiDAR. So you can see that we added extra range gates before and after the ridge. So we had range gates, so measurement points starting at 700 meter distance from the LiDAR, going up to about 2.6 kilometers. And looking at the data, so the original data, the raw data, you can see, especially in the far range, there's a lot of scatter, and which is obviously not, so we didn't have enough backscatter, so the signal quality was not good. And if you then look at the lower two plots first, where I filtered the data by the CNR, the carrier to noise ratio, which is most commonly applied, we can see if we use a minus 27 dB threshold, we remove some of the scatter, but there's still some data here which obviously doesn't look right, where we have spikes in the data that is obviously data that is not valid or not correct. And this we would remove if we further reduce this threshold going to minus 24 dB, but then we also start removing good data and really decreasing our range. So we developed a filter that is based not on the CNR value, but on just on the line of sight velocities. And we just assume that there's a certain continuity in the wind speed, that if you have one range gate, one measurement that says it's 10 meters per second wind speed, and the next one says it's the opposite direction, we would say, okay, there has to be something wrong. So we're calculating the moving average along the line of sight and azimuthal directions. And if we have then measurements that exceed this moving average by a certain threshold, we say, okay, this is a suspect, we should better remove it. And this leads to much better results. So this is this filter plot here. So we significantly increase the range to the minus 27 dB threshold filter. So we cover actually all the way up to the ridges. And it also remove all the scatter points where we see, okay, something is not right. And also at this one location here, we actually remove also the hard target measurements that caused by the presence of the wind turbine. No, actually there it's 100 meter measurement masts, which is causing hard target reflections where we cannot measure. So we found really good performance of this filter. We just basically looked, but just by looking at the data, we had no proper way until now to validate that its performance. But if we use the thresholds, how we tuned them, we on average reach 20% more data compared to minus 24 dB filtering. And having the data filtered, we then combined the data of the two scanners along one ridge to get the U and V, the horizontal wind components. Which brings me basically to the next topic, the data availability, which gets an issue the more and more systems you need for one scenario. And we look at the signal at this line, so availability of the single systems, just the system availability, no filtering or no data quality yet. We see it's ranging about 70% or better, but if you then require that, if you then look at the reconstructed wind speeds where we need 2 scanners, it drops to 80 and 50% at the northeast and southwest ridge. And if we then also are interested in having data available from both ridges at the same time, we are already down to 40% of data. And then after filtering this data and also requiring of having wind speeds above 3 meters per second, which are more significant for wind and the field of wind energy, we actually end up only with 23% of the data that can be used basically to analyze it, which, yeah, is probably one of the biggest issues with scanning lidars, that still the availability of data or the system availability is a problem. But nevertheless, we can still use the data to get some interesting information out of it. First, we started just to be confident that we're measuring, that our measurements are correct. We compared the data to the 100-meter towers, so the 80-meter level at the 100-meter towers, and we found good correlation for both towers. And so there's obviously some variation there. It's not perfect, but we have to keep in mind that that sonic and lidar measurements are not co-located. We actually had to use measurements that are 40 meters away from the masts to not have interference with the guide wires of the towers. And also, as you can see from the plot, the towers are not exactly located on the transect of the lidars. So we measure a bit to the side, the masts are not exactly at the right distance from the lidar where we actually measure. And the measurement volumes are completely different. We have a sonic measurement volume of 10 centimeters compared to the measurement volume of 30 meters to the lidar. So keeping all these factors in mind, we consider this as a good correlation and are confident that we can trust the measurements. And maybe just to get a better feeling where we measure, I made this side view on the data. Seeing here the terrain, and then in blue the measurement points of the lidars, and then the vertical profiles are the tall masts that are located on the ridges. And now looking actually at the data to analyze it, I started segregating it by wind direction and stability. So here we see only data for northeasterly flow, the left plot for unstable conditions, the right plots for stable conditions. And okay, there are also numbers, but we just have to look at the colors on this projector. We cannot see the numbers. So the data is normalized, so the colors are normalized to the mean wind speed along the upwind ridge, which is here the northeast ridge for northeasterly flow. And most obvious what we see is we have much higher wind speeds at the downwind ridge. At the southwest ridge, for both situations, unstable and stable conditions, it's more pronounced during stable conditions where we have up to 40% higher wind speeds downwind. And also we have a change of wind speed along the southwest ridge. So for both situations, stable and unstable, we have lower wind speeds in the southeast and higher wind speeds in the northwest. And this trend is about 20% difference in relative wind speed. And looking at the northeast ridge, we see there's some variation along the ridge, but there's no obvious trends, only that we have higher wind speeds at the southeast end of the northeast ridge for basically stable and unstable conditions. And if you then also look at southwesterly winds, we see, so now I normalized the measurements to the mean velocity along the southwest ridge. And here it's interesting, we see that During stable conditions, we have again higher wind speeds at the downwind ridge, which is actually the ridge that is lower in elevation. So we have higher wind speeds downwind at a basically lower height. And we don't find these phenomena during unstable conditions, which basically leads us also looking here that we have higher speeds during stable condition in both cases, which shows us this impact of these atmospheric waves, which you could see at the beginning in this one plot. They're really causing basically most situations an upspeeding of the flow, a concentration of the flow speed, and then higher wind speeds the further downstream we are looking.
Robert, you might have already stated that. How do you determine the stability for your specification on stable stability?
So here I'm used the Richardson number calculated at the upstream mast, where I'm not using the wind speed, so I'm not including shear. I'm just using the 100 meter wind speed and saying we have zero wind speed at 0 meter to not get this negative shear and overspeeding effects into this determination of the stability. And as it's really hard to not really define how to have where the limits are, I'm just saying here basically stable is everything greater than 0 and unstable is smaller than 0. So we have mixed in neutral conditions, which we only expect during short transition periods. We expect that basically 90% of the data or even more is stable, unstable, that we only have short transition periods where it's neutral.
So is it a Richardson number at a certain height, or is it a sort of a mean value of that Richardson number?
I used here, I calculated the gradient, the temperature gradient over, I think 20 to 60 meter. But I would have to check that. Okay, so summarizing these observations, if you take all the data, all atmospheric conditions or wind directions, we find that wind speeds are 10% higher at the southwest ridge, and this is kind of the same along the whole ridge. But then when we segregate the data, we actually see these changes which I highlighted before, that we have this change along the southwest ridge of 20% in wind speed, and that especially during stable conditions that we have higher speeds at the downwind ridge of mean wind speed up to 1.8 meter for the southwest ridge. And during unstable conditions, we find higher wind speeds at the southwest ridge actually for both the wind directions. And looking at the mass data, we find very high inclination, flow inclination angles, positive angles at both ridges during unstable conditions, and also negative or basically almost zero, negative to zero shear, which kind of highlights this complex, the interaction of flow and terrain. So after we got this finding, we were interested of what models would see. And we were lucky that Johannes Wagner from DLR performed WRF-LES simulations for the whole period of the IOP period, so 90 days. And he ran his model in 3 domains from 5 kilometer resolution down to 200 meter, and the 200 meter domain was the LES domain. You can see them here on the right, and the plot in the lower right corner is just zoomed in on the ridges in the third domain. He used Korean land cover data, and he ran the simulation twice. Once just with surface roughness, and then he also added forest drag in forested areas. But don't ask me too many details about the simulation, I'm not a modeler. There is an overview paper published in the ACP journal where he's describing all the details. So we were more interested in how does the model compare. And so it was not super obvious that it can be compared at all, but we should start, if we're taking all wind directions and all the data and average so we used only the simulation data that was available, or that for the periods where we had measurement data available, and we found that the simulation without the forest drag added compared quite well if we just looked at the mean along the two ridges, and we found that it's slightly overestimating the wind speeds by 6.5 and 4.1% at the southwest and northeast ridge. And looking at the simulation with added forest drag, we found that it's significantly underestimating the wind speed by 30%. But then looking a bit more into detail in the statistics, we found that having the forest drag, actually the correlation coefficients improved. And looking here at just southwesterly winds, just for example, and for stable and unstable conditions, we see here in blue the simulation with forest drag, and in red the without forest drag, and then in yellow the lidar measurements. So we see these lines don't overlay at all. But what we can see is that basically the changes that are predicted along the ridge are looking more similar to the measurements for the simulation with forest drag compared to the red line where he ran it without forest drag. So there's a lot of fluctuations along the ridges and also steep changes which we don't see in the data. And then it looks much better, the comparison, if we ignore the huge bias for the simulation with forest drag, the blue line. And the bias could be a source of that. Use the tree height in the forested areas. There was basically twice the tree height of the real trees. So it probably was slowing down the flow too much, but still we saw a positive effect. So I think he's aiming now to run the simulation again with a more realistic forest height. And concluding all of this, we could see that basically it was a successful demonstration that dual Doppler systems can be used for wind resource assessment in complex terrain. We in future have to work on the availability of the systems, that they run more stable, and so that we have basically more data available. And that flow simulations really highly rely on the characterization of the surface friction, and that it's important to have the very high detailed data to get it right. And this work is now in preparation to be published in the Wind Energy Science Journal, which we will hopefully submit the paper soon, within the next 1 or 2 weeks. And yeah, you can see the co-authors, my supervisors, Nikola Vasilievich, Jakob Mann, and Johannes Wagner from DLR, and Steve, who helped me a lot with the analysis of the mass data, and also at figuring out how to interpret the lidar data I was seeing. So next I want to move into a study of recirculation zones that we observed and also anticipated to form behind the ridges. And we mainly focused on the questions of if we can see recirculation into two-dimensional phenomena, or if there's a change along the ridge, so like a third component. So basically, does the recirculation zone look the same along the whole valley, or is it changing along the valley? And then what is the impact of recirculation at possible locations, so basically at the ridges, at downwind locations, at the downwind ridge. And this work has been published in the ACP journal, and it was also prepared with my supervisors and Julie Lundquist from CU Boulder. So we used the same lidars as in the previous study. Basically, we brought 8 of these scanning lidars to Portugal. And in this study, I used 6 of them that carried out RHI scans in basically perpendicular to the ridges, from both ridges, so we had them in both directions. And we had a scanning range of 3 kilometers, range gates, measurement points every 15 meters, and one scan took 24 seconds. And again, the same 30 meters averaging volume. And again, I made an animation, so it's showing we basically covering with our scans the entire space within the valley where we want to see the recirculation zones. So this was perfect way to assess these. And here we filtered just by a CNR threshold filter, as we were not really required to have like a far range, because recirculation zones were expected to occur within like 1.5 kilometer away from the lidar, so we didn't have a high requirement on range. And so CNR filtering, and we removed obviously hard targets. Then to analyze the data, we averaged the data again over 10-minute periods. 10-minute periods is an average time that it's very often used for wind energy applications, so we stick to this. And then for combining these scans, we didn't interpolate in between the scans as they had different elevation angles, so there was no obvious way to interpolate, but we gave priority to the downwind lidar, because the downwind lidar will cover better a recirculation zone that is happening upstream. And then to detect the recirculation zones, I have here an example plot. We have here wind direction from left to right, and then in blue you basically see the recirculation zone area. So we defined them by the zero velocity contour in the plot, which gave us basically the area of flow that is moving in the other direction. And we had a requirement that the speed should move by the reverse wind speed should be 0.5 meters per second within the recirculation zone to be counted as recirculation period. And looking at the data again under the same Richards number as I used for the previous study in southwesterly and northeasterly flow, we see, comparing here the bars in blue periods with recirculation to periods without recirculation, that we find more recirculation cases during unstable and neutral conditions. And then moving a bit further, segregating the data also by the 3 different transects that you could see before. Here again is like an overview map. So we are looking here now at the blue transect, most in the north of the experimental site. And what we see here is basically recirculation becomes more likely to occur with higher wind speeds. And there is also, when we compare the 2 ridges, the ratio of recirculation to no recirculation cases. So we see that we have a higher ratio at the southwest ridge. So we find more recirculation cases at the southwest ridge. It's more likely to occur there. And then moving down in the map through the transects from the red to the black one, it's mainly interesting, or most interesting, to look at the ratio which is changing. Here from 3.6 to 1.2 to 0.6. So we basically see that recirculation in the north is much more likely to occur than all the way in the south. So it's actually a strong change along these ridges, which we didn't really expect in the beginning to find. And to sum up these findings, we found a higher probability of recirculation for stable near neutral and for higher wind speeds. And then we found this change along the ridges. And this change is most likely connected to, or the most obvious way how we see why we can find this change, is that actually the elevation profile at the three transects is very similar at the ridges. There are almost no changes, but then we have these changes here within the valley. And we find that for the black transect, which actually is the lowest, like the highest elevation, but doesn't go so deep inside the valley, we find less recirculation. So this might be also like very possible to basically suppress the formation of recirculation zones. At least the recirculation zones that we detect with our LiDAR scans. Of course, we cannot scan very close to the ridges because there will be backscatter interference of the measurement volumes and the trees or the surface. So we measure only 30 meters away, so we can only detect recirculation zones of a certain size. But the size of recirculation zone we can detect is changing along these transects significantly. So to conclude the talk at all, we find that scanning lidars are very useful to investigate flow in complex terrain, especially for capturing flow phenomena that are basically hard to investigate if we look at single profiles. So we actually, in case of the recirculation, we were able to determine the size of the recirculation and the extent, the height and speed within the highest point of speed within the recirculation zone. And for the case of resource assessment, scanning lidars are a huge opportunity to really capture the spatial variability of a measurement site and take measurements at multiple locations. And which was obvious, it's like the flow is highly complex and it's very affected by these different phenomena that we see in complex terrain, and especially at the Perdigão site. And who's interested in the measurement data? It's available online for the whole period of the experiment. We converted it to the netCDF format, so it's should be easy to work with it, or easier than it was before in the raw data format. And this is all what I had for today. I'm happy to take your questions.
This seems like a difficult problem, your first part, because you showed the results of LES models that one would expect would actually do fairly well, if anything would do well in complex terrain. So presumably your wind atlas is actually using lower resolution data, and yet you're trying to estimate the amount of wind energy that is available over complex terrain. So, and you showed wind speeds that often differed by a factor 2, so the energy probably goes like a factor 4 or so. So how good is the new wind atlas going to be?
So there's now a comparison running. Jakob mentioned it in his talk 3 weeks ago. So they got access to, I think, 200 masts spread over Europe. So they're starting to compare there, and they see actually quite low biases. So, and for this comparison, maybe I should also point out that we see, as we can see here, we have here compares by 6.5%. So the more, and this is when we take all the data, and the comparison always looks better the more data we take. And then if we reduce basically segregating the data in different atmospheric conditions, the amount of periods reduces. And then it also gets much harder for the model to predict exactly at the right time the right wind speed, which is like mitigated when we look at more periods.
But when I look at the figure there, that's where I get my factor 2, and yet you're saying 6.5% there. So I don't quite understand that.
Okay, so this 6.5% is if we take all the measurement data that we had, like all the 10-minute periods. I think we had 507 10-minute periods. And then here we just look at, out of these 507 periods, we only look at periods with southwesterly flow and unstable conditions. So it's a very small subset. So it's very important there, actually, for the model also to get the timing right. And the wind atlas, as it's more concentrated and give like an overview of the wind resource, will give more, is more interested in mean wind speeds. So it's not actually, I think, not giving like time series of data. So that is an issue in this comparison. And obviously this large difference was pretty likely caused by this forest drag that was completely overrepresented. And this is like a simulation, was not included in the wind atlas. So these are two different model ones.
I do have another question, but I keep harping back on this, stability. How do you determine the stability? And I assume that the comparison between the model and the observations, the same set of criteria for stability were used for the simulation, right? Or you went from the observations and you selected the periods and then you looked at what the model predicted for those periods of time?
Exactly, that is what we did.
But
we took the observations and the observational periods where we actually had data available, and then took the exact same period out of the model data.
I see.
And we didn't look for like similar situations.
So you have no idea what sort of stability was the model predicting at the time?
No, we didn't investigate that. Yeah.
Okay, so that might be the reason why there is such a large discrepancy. And again, going back to the stability, it's really important in these studies, when you're looking at complex terrain flows, that you do take a profile sufficiently far upstream of the terrain, because that is an undisturbed profile. And I don't think that you quite in Perdigão experiment design, have that luxury. So
no, we don't really have it.
Yeah.
But also, I mean, obviously
the profiles you are taking are already modified by the complex terrain, so there is a catch-22 there.
Yeah. But then we have also the issue that the ridges were obviously like one of the largest terrain features in the area, but also the terrain surrounding the ridges was also complex.
Exactly.
So it's really hard to define, okay, where do we actually take our profile for stability?
My advice would be to go with something that comes from an independent source, in determining whether it's stable or unstable, even if it's, God forbid to mention, reanalysis, so.
Yeah.
But my question is actually about these recirculation zones. This is actually fascinating to see them. Do you have have you developed a feel whether they are all the result of separation from the peaks, like the separation from a bluff body flow separating from the top of the ridge, or actually some of them might be wave-induced recirculation zones? So have you looked at the locations, in other words? Have you looked at the locations with respect to the ridges?
Yeah, so the majority of cases is where it's actually flow separations, especially if you look at near neutral and unstable conditions. But then we also we detected recirculation zones during very stable conditions, where the recirculation zone was forming under like a wave, atmospheric wave that was forming. And we actually tried a bit to separate these cases from our analysis, because I think there was a criteria, I have to check that basically said, okay, this separation, it has to be a separation-based recirculation zone. Because we basically can find reversed flow speed areas if we have the waves like at every part along the transect. We can have them right in front of the downwind ridge or like in the center of the valley.
Both of them are the result of the boundary layer separation.
Yeah.
But the pressure gradient is induced in different ways. So pressure gradient forcing that separation.
Yeah.
In neutral flow versus the stable flow.
Yeah, so we more looked at form drag cases there.
Any other questions?
So now that you've done this detailed analysis of the wind flow in this region, is it premature to ask in your resource assessment where you would put a wind turbine? Would it be in the north or the south? Or another way is, what are the optimal conditions that you have found where you could put a wind turbine.
Yeah, I mean, it's obvious we only investigated the resource along the ridges, so it's already obvious that they should be on the ridges. And then it's like, safe or easy answer for me, it should be on the southwest ridge. There is already a turbine, so they, even without these complex measurements, they figured out the southwest ridge is the better one. Or maybe it was because of access reasons, it was easier to access the southwest ridge. But also now, basically, it's reconfirming that our measurements, that the turbine was placed on the right ridge. And as you could see also that the mean wind speeds were 10% higher at the southwest ridge. I showed it in one of the slides. So this is basically the factor of where to put the turbine. It's always where the wind speeds are highest. And obviously, you would also try to mitigate some of the load cases induced by a very complex flow on the turbines. So you would maybe try to find a location where the shear and the wind profile is not as strong. But this we found actually is quite similar at locations that would be suitable for turbines.
Other questions? Okay, then let's thank Robert again.
And if you're interested in the slides, I already uploaded them to Zenodo, and you can track them with the DOI.